Hey everyone, I hope you're all good. So I'm Tswelopele Moshe, but I usually just go by Tswelo because, well, every time I meet someone new, I'm like, yeah, my name is Tswelopele. They go like, yeah, but how do you pronounce it? Then it turns into like a whole 5-minute conversation. So just go by Tswelo. You guys can call me that. So today, well, actually, before I get to my talk, I'll just uh, briefly tell you who I am. So I'm actually, I work now with an MTN group. I used to be a cybersecurity consultant at MWR. And right now I'm actually also a student. I'm working within the intersection of information theory and automata theory to come up with automated ways of discovering side channels within computer programs. But that's not what I'll be talking about today. I'll be talking about something else that's kind of completely different. It will be about just a little thing I've kind of been trying to work on. So MITRE Engenuity every year releases these evaluation results, kind of measuring how well different EDR solutions actually respond to attacks within the ATT&ck framework. And on this, what tends to happen sometimes is these different EDR products come out as, oh no, we won this, and we did better than all these other EDR solutions, and it kind of boils down to the way they chose to interpret the data. But MITRE does release a few metrics to help consumers actually do this interpretation. And I was just thinking about, okay, cool, can I actually find one metric that consolidates across all these metrics, including some of the other ones that people in the community have actually worked on? So this is really just a culmination of that work. And I mean, it's a work in progress, but this is more just like a progress update, what I've come to. So just before we get into the evaluations, so these evaluations are carried out based off the ATT&ck framework or the ATT&ck framework by MITRE. And basically what it boils down to is really classifying what we know about adversaries into TTPs. So the tactics, the first T in TTP is really what the goal of an attacker is. And then the technique is how an attacker actually goes to achieve that. Procedure are just the step-by-step instructions of actually, well, step-by-step descriptions of achieving the technique. And what's nice about the framework is that really it provides a nice consolidated taxonomy so that different groups of people can actually speak the same language when they share threat intel. And what's also nice is that really it's open and really anyone can actually contribute towards this framework. So one of the reasons why it's really a reasonable thing to keep track of or to really communicate adversary intel through TTPs is because it's really hard for adversaries to change these. I mean, historically, one of the ways would actually maybe try to go do threat hunting within a digital estate is maybe look at, the binaries that are there, hash them, but that's easy to change. Just flip a byte or add a byte. And now you've really evaded detection. Or maybe if you want to keep track of different types of adversaries that could be targeting you as an org, looking at the IP addresses, that's easy to change. The domain names they use, also quite easy to change. But then as you go up this triangle, it starts to get a little bit challenging. And there at the top, the different tactics, techniques, and procedures that threat actors use are pretty hard to change. Because even if you do decide to go, okay, cool, I'm just going to maybe decide to write my malware not in this language, maybe another one, but at the end of the day, you might just actually still be calling the same Windows APIs, and fundamentally that kind of boils down to the same techniques, which roughly translates to probably the same tactics. So just for an example of these TTPs, so if you actually go onto MITRE's website, there's quite a few examples of the different techniques. And the whole flow of going from tactic to procedure is just asking the question, how? So say maybe an adversary wants to prev-esque within a digital estate. What's the one way they could do that? So the one technique is maybe through process injection. And how can they do that? So if you actually go and scroll down this exact page, there's a list of procedures. And this is mostly based off threat intel that exists out there, right? It's not a be-all, end-all of all the different types of ways one can achieve a particular technique. And one way to achieve process injection, I guess, is to just, I don't know, get some malware. So there's this malware called Avenger, which could inject shellcode into SVC host, because as you know, SVC host runs in the system context. So you can actually run your own shellcode within that context to get privilege escalation. So from MITRE to MITRE Engenuity, they have the Center for Threat-Informed Defense. So one of the things they do there is really they take a lot of the information that exists out there from various intelligence sources, and they kind of collate it. And one of the things they do, so if you actually go into their repo, there's one of their repos, there's the adversary emulation library, and this really contains the different sort of emulations that they've built up. So like setting up the infrastructure, the actual source code you could use to actually run this on your own, to actually set up the different sequences of techniques of well-known adversaries, or APTs, actually. And the one we'll be focusing on here to go through this metric that I've sort of developed is the wizard spider attack scenario. So they actually ran this in 2022, and it's based off some of the techniques of the wizard spider APT group. So fundamentally what MITRE Engenuity does is they take this threat intel information and they ask the question, to what extent do EDR solutions actually respond to well-known adversarial techniques? Because I mean, at the end of the day, if you as an organization are going to buy an EDR solution, you would at the very least, expect them to protect you against well-known threats, right? So that's kind of like a bare minimum. And so as I've just alluded earlier on, we'll be looking at the 2022 wizard. So in this actual evaluation, they ran both wizard spider and sandworm. So those evaluations are named after their respective APT groups. We'll be looking at wizard spider in particular. So just a brief overview. So this is actually a diagram that roughly translates to how the scenario looked like. It's the usual, somebody downloads, or somebody gets phished, they download a Word document, they enable macros, the macros load a malicious, so it loads malicious code, which further downloads other malicious software. That software basically starts enumerating the environment, and then establishes persistence, and then goes on to the next host, and then starts enumerating again at this level, starts enumerating the domain, and at that point within the domain does privilege escalation, and then deletes all backups, and then it actually starts encrypting all the files that exist within the domain controller. So just to go through the different detection categories that MITRE Engenuity introduces within this particular evaluations. Every year they kind of like playing around, so I know within the next evaluations they're going to introduce a detection category that focuses on false positives, which is actually would be very nice for this. So just to give a brief rundown, so from top to bottom, there's an increase in the level of granularity within the detection. So for example, if we start with telemetry detections, if an EDR makes a telemetry detection for a given attacker technique, what that actually translates to is that, sure, the EDR has some level of log visibility within what's happening within the environment. But as you go down with the general detection, that means that, okay, cool, the EDR can now actually make some level of inference based off intent as to what's happening. So that's where you start actually having malicious or abnormal events being detected based off the ingested logs. And then going down, now the EDRs can detect, okay, there's a goal here of something that's happening with the tactic detection and with the technique. Not only does it tell you something bad, there's a goal, but it also tells you this is how they're doing it. So MITRE Engenuity releases some metrics to help people who are looking at this data, to help them actually interpret what the data means. So the first metric they release is an analytic coverage. So all that this tells us is the proportion of the detections made the above telemetry. So the whole point of naming it analytic is because it will allow, I guess, blue teamers to go and do something of value. So in terms of analyzing what's actually happening within their digital estate. But what's important about these metrics is what's in the denominator there, which is it's over the total amount of visible substeps. So this is actually key because visible substeps count all telemetry, general, tactic, and technique detections. So an EDR can have very poor visibility, but a very high analytic score. So if there aren't actually, if maybe throughout an entire attack scenario, there's maybe 10 steps, and an EDR makes 5 total detections, but all those 5 total detections are above telemetry, then they have an analytic score of 100%, but they missed 5, actual detections, and those could be the big ones, right? So this is one of the ways that different EDR products can go like, oh, we score 100% in analytic coverage, we're the best, but you don't have good visibility. So telemetry is just the number of, I guess, total telemetry detections, which is basically, just go count how many of the detections were telemetry, but that's also minus the tactic and technique detections. And then visibility is just the sum of those two. So these authors, so most of them are actually from Singapore, they wrote this nice little paper, in some sense, decoding the MITRE Engenuity Att&ck enterprise evaluations and analysis of EDR performances in real environments. So they introduced these 3 metrics. So I'm going to start with the detection quality. What this really wants to measure is to what extent is the EDR usable out of the box, right? So all that takes is the proportion of the number of visible substeps without negative modifiers. So I didn't actually talk about negative modifiers yet. So these are detections made that were either delayed or there had to be a configuration change for the detection to be made. So you go count how many of those detections were made without these modifiers, and you just divide it by the number of total visible substeps for the actual EDR product. Yeah. So the other metric they introduced is detection confidence. So all that this really wants to measure is to what extent are EDRs actually making more technique detections than there are any other form of detection. So that's why there's a higher weight on the D_TE. So those are the number of detections made with technique detections. So one of the other metrics they introduced is what they call whole graph analysis. So in this whole graph analysis, they take a variety of, so maybe computations or processes, and they look at what was actually happening within the attack scenario, right? And they draw what we call a base graph from that, and the nodes are the different computational units, and then the actual edges are the technique ID associated with moving from one computational unit to the next. And they take this graph. So basically in this graph, it's the wizard spider scenario. So Explorer EXE opens Word, Word loads adb.vbs since with macros enabled, and then that eventually leads to CMD being open, and then that opens up PowerShell, loads the DLL, and then the DLL goes and actually runs some Windows APIs, and then Outlook DLL is downloaded, and that scrapes for creds, and there's also C2 called the T10710001. So that's the technique ID associated with a program communicating out to a C2 channel. So what they do here is they take all these edges within the first graph and they turn them into nodes within the second graph. And the second graph, the new edges are what they call causal relationships between the different technique IDs. So these could either be data transfer or operational flows. So now they do analysis based off this graph, and the whole intent behind this graph is to see how well EDR solutions can actually make inference along a chain of steps. So if maybe an EDR solution failed at making detections within the first 2-3 steps, you would expect them to actually do better within maybe the 4th step. I mean, that doesn't necessarily mean that they're actually doing inference on a graph, but it's sort of a good way of measuring to what extent are they actually making detections linking previous somewhat, suspicious activities that are happening within an endpoint. But so this particular analysis was actually quite, first of all, it was limited. So I'm not exactly sure how they rederive this graph, because when you actually go to MITRE Engenuity, if you go read the actual attack steps, this is missing quite a few attack steps. So I guess this is because I was actually trying to reproduce the results. And then the other issue was, I thought, okay, cool, they have this cool graph. I wonder if you actually start using all these other metrics that they had and use them as weights on this graph, could you come up with one consolidated metric to actually measure all these other different elements? And the whole idea there would be, to what extent do EDR solutions actually infer the actual attack graph for the scenario? So this is how I built my graph. So the base graph is 2 entity subjects, which would be either process, basically a process, and the edge would be the attack technique. And for the base graph, all the weights are 7s. So the EDR reproduced graph will be built based off the data from MITRE Engenuity. And say, for example, if maybe Word opens a DLL and there's a technique ID, so the weight would be given by the detection category, and they'll be penalized for a modification category. So if it's either delay, configuration change, or user consent. And so with that in mind, this is the base graph for Wizard Spider. It's quite a lot, but to really boil it down, what's happening here is somebody gets fetched through a macro in Word, and at this point, so what's happening here is basically there's enumeration going on, and further down here, which is really the nice part, is this Ryuk malware is used to perform process injection onto Notepad and starts actually going encrypting all the files. I'm not sure if it was actually process injection or was it Halloween. But yeah. So it actually used, what was it? Door.io for that graph. And at that point, I was like, oh, should I now go do this manually? But I actually discovered, because if you use Door.io, one of the things you'll discover is if you just click on an object, if the arrow is connected, you can start moving it around, which means that the program can somehow keep track of, this arrow is logically connected to the shape. So it turns out then that Door.io actually encapsulates that within a graph structure as well, and you can just save that as an XML, and you can just turn that graph into a Python network X graph. Just a little bit on graph. So a graph is basically a tuple with the sets V, W. So the V is really all the nodes, and the edges are I guess it's a subset of V cos V, which denotes the connections between all the different edges. And then the weight is just an assignment of some value on all these edges. So one other thing we'll need, because at the end of the day, what we want to be able to do is we want to be able to compare two graphs and ask ourselves, how similar are these two graphs? And there's many ways of doing that. But one of the things we'll first need to do is we need to assign weights to these graphs, and we need to first talk about what we call an adjacency matrix and a degree matrix. All that this is really, it's a matrix with rows and columns, which are just the weights. So if maybe you have a graph where the first edge has a weight of 7, then at the first row column entry, you'd have 7. And the degree matrix just describes the connectedness of the different edges. So what you can then go calculate is the Laplacian matrix, which is just the the degree matrix minus the adjacency matrix, and you can just easily go do that with network X and Python. So what I first actually wanted to do was use the graph edit distance. It's really the most intuitive way of actually measuring how two graphs are similar, right? So what's nice about graph edit distance is that there's an implication that if two graphs have a distance of 0, then they're isomorphic, which means for all intents and purposes, they're the same. So this is what I actually really wanted to use. It's sort of like the Hamming, for anyone who's done the Hamming or knows about the Hamming distance, it's kind of like the same idea, but on graphs, not on bit sequences. But it turns out that it's actually very expensive computationally. The more nodes you have, as you can imagine, the more nodes you have, the more computationally it actually scales exponentially. I think at around 10 nodes, it actually almost becomes too slow for a normal classic computer. So then what I did was, there's one metric that you could use to actually measure the distance between two graphs. So once you have the Laplacian matrix, you can go and calculate its eigenvalues, and then you can go actually find how far apart these eigenvalues are. What exactly this means within an attack graph, I'm not sure yet. I mean, in some other contexts, say maybe physics, within a physical context, it tends to be quite easy to interpret what these sort of means once you've actually modeled a situation. In this, not so much. So I did further analysis to actually try to come up with maybe what could this mean. So the Laplacian spectral graph distance will denote it as LSGD from now on. And so one thing you could ask yourself is, okay, cool, does this maybe measure visibility and to what extent? And so I just really threw this to get a rough idea. And it doesn't look like there's any clear relationship as of yet. I was like, okay, cool, maybe it's not that. Maybe it's the confidence score. And here there's somewhat a bit of a clear-ish relationship. There's maybe like sort of like a straight line going through there, but with Secure and Trend Micro, they're just on the side chilling, who knows. Maybe it's the detection quality. This looks promising, but it's not really promising for my initial intent, right? Because my initial intent was to capture all these metrics into one metric, but we'll see. Oh yeah, so the next one was analytic coverage. Same here with Secure and Trend Micro, just chilling there by the corner. So what's happening with these two? So it turns out if you actually go look at the data, with Secure and Trend Micro are very different in terms of how they actually engaged within the evaluations. So you'll see with Trend Micro, they were very hands-on. So they had to do 14 configuration changes for there to be any reasonable detections, and there were 11 delays within the detections. And then with Secure, they were pretty much hands-off, and there were no delays. So it seems like this metric is actually there's a weird bias going on towards how much these EDRs actually engage. So maybe the problem here was we've confounded managed detection and response with just straight out of the box EDR. So, well, what if we just really added more data? Would that solve a problem? Not really, actually, just makes it worse. Yeah, so I decided, okay, cool, maybe let me just go and measure the correlation between this LSGD metric and all these other metrics and see, and just quantify the relationships between these two. So there's the usual Pearson correlation metric that we're all used to. I didn't use that one here because the assumption there is that first of all, each data is assumed to be distributed normally. So when you want to go and calculate your error bars, that's the assumption you'd make. And then the next assumption it makes is that there's a linear relationship between the two, but I didn't want to make those assumptions off the bat. So I was like, hey, cool, I just want to measure if there's any monotonic relationship between the two. That is, if one one of the metrics increases, then the other one also increases. And also if one decreases, the other decreases. And the Spearman rank correlation test kind of tells us that. And looking at these results, there's an implication that there's quite a weak relationship between pretty much almost all these metrics and the LHGD. But I think what's nice, or the lesson learned behind this, is that so we've somewhat came to a place where, because just to backtrack a bit, if I did, one of the trivial things to do, if you do want a consolidated metric for kind of bringing all these together, is just take a weighted sum, right? Well, why not? But then the question is, okay, cool, what weights do you put on each of the other metrics, right? Then that has to, maybe as an organization, you could put weights on what you care more about, cool. But with this approach, what I wanted to try and capture mostly is, cool, there's this attack scenario going on, and we have this picture of it that feels intuitive as a human to read, and can we map that onto something quantitative that we could go use to actually rank how these different EDR products did within the attack scenario. And so I guess for me, that was really the intention. And really what we've learned here is, okay, cool, there's this graph-based approach. Maybe if you just tinker a bit with the weights, you could get something that's a bit stronger. Yeah, so basically just to conclude, we've just really highlighted the process for designing a potential candidate for a consolidated metric to judge the performance of different EDRs. Maybe, and so this actually, the one thing that I actually found was under some certain regularity conditions, it can work well. So if you take a subset of these EDR solutions, this very same metric could actually work well in consolidating all the other metrics. But for all of them, you need to be very careful because of how the different EDR vendors engage within the assessment. But this, in my opinion, is promising, and really one of the next steps within this is to try and actually understand within the context of the attack graph, what does it mean to take the eigenvalue of the adjacency matrix? What does it mean to take the eigenvalue of the Laplacian matrix? And from there, I guess it'll be cool to, find out. And that's me.